Good afternoon and welcome, friends. Welcome to this unique initiative of Indi Energy of creating a knowledge series for the lover of battery makers and the enthusiast to know about different kinds of batteries. So, on behalf of Indi Energy's board members and Indi Energy team, we welcome you all. This is an interesting journey, interesting opportunity we have to understand what are the alternate energy storage system we can build for the future sustainability and future development of the country and as a world as a whole. We are going to take you through a small video, 3 minutes video about the journey of Indi Energy, its aim, its goal, to understand that where we are in terms of the futuristic vision, what we have, and where we want to take this organization forward. So please, let's take a couple of minutes to look at actually the video, the journey of Indi Energy.
We are indigenously developing our low-cost, safe, and high-performance sodium-ion batteries that are made from bio-waste or agriculture waste like paddy straw or cattle manure, and earth-abundant materials like sodium, reducing our dependence on scarce elements like lithium, cobalt, or nickel, which are essential components of import-dependent and expensive lithium-ion batteries.
At Indi Energy, a startup incubated at TIDES IIT Roorkee, have invented and patented technologies that converts cow manure and paddy straw into battery-grade carbon material, which act as electrode material for sodium-ion batteries.
Indi Energy's sodium-ion battery will not only reduce India's dependence in importing scarce elements like lithium, cobalt, and nickel. It also helps in creating additional income source for our farmers. The farmers can sell their disposed extra to battery-grade carbon manufacturing company like us.
To make India self-reliance, Indi Energy Technologies has started working in the area of sodium-ion batteries. We have invented new materials, cell technologies based on agricultural waste and bio-waste material, and the performance of our cell is at par with lithium-ion batteries with a low cost. So we believe that our technology can immediately replace lithium-ion batteries and lead-acid batteries for whatever the application we can look for.
Thank you, folks. I think you guys would have got some peek into what we want to build, what we want to work on. So today on this interesting deliberation, we have 4 great scientists in the panel. We have our very own Dr. Yogesh Sharma, who is the R&D head of Indi Energy and professor in IIT Roorkee. We have Professor Prabir Badponda. We have Professor Ruaji in Ineda.
Okay, sir.
Yeah. We have Professor Reja Yunesi from Sweden. So we have a galaxy of speakers around, actually, from the global arena to discuss and deliberate around this issue. So I'm going to invite, the Professor Yogesh Sharma to talk a little bit about actually the topic and introduce the panel so that we can take it from here. Over to you, Professor Sharma.
Yeah, some problem. I welcome, hope I am audible. I welcome all the lovers of batteries and their interest in lithium-ion batteries, sodium-ion batteries, and so many batteries. I mean, I believe all are lovers. So as the title of this webinar is, we are going to reveal something about sodium-ion batteries. And in this webinar, we will be discussing why a sodium-ion batteries has evolved in the last few years, and what actually sodium-ion batteries. And I'm sure many of us would love to know what are the different components we use in sodium-ion batteries, how does it work. So to reveal everything about the sodium-ion batteries and its technology, today, as Bhavani ji said, that we have well-known researchers in this area. So first speaker we have today, Reja Yunesi, is an associate professor at Engström Advanced Battery Center at Uppsala University, Sweden. And founder is one of the well-known company of Eltris AB, who are working exclusively in sodium-ion batteries for many years. So Professor Yunesi had worked as postdoctoral fellow at Technical University of Denmark. He received the PhD from Engström Laboratory in Uppsala and MSc from Royal Institute of Technology, Sweden. The research focus of Yunesi team is an interfacial reaction in rechargeable batteries and materials, development for sodium-ion and lithium-ion batteries. Being a founder of a company who are exclusively working of sodium-ion batteries, being a one of well-known professor from Sweden, Professor Yunesi has done extensive work in this area. So I will about sodium-ion batteries and the space he's working in this area. Professor Yunesi, please.
Hello, do you hear me? Yeah. You hear me?
I request everyone, please switch off your mics so that we can listen Professor Yunesi. You please switch off your mics, please.
Can everyone actually put their phone on mute?
Do you hear me? Hello.
Yes, yes, very much, Professor Yogesh. Yes.
Very good. Thank you very much for this nice invitation. And I'm sorry that I have lost my voice a bit in last few days, but I think I will manage to give this presentation. Again, thanks to Indi Energy for inviting me to give this presentation. It's my pleasure to talk to you guys. And thanks for the nice introduction also. My name is Reza Younesi, as you mentioned, and I'm associate professor at the Department of Chemistry Armstrong at Uppsala University. So it's quite short presentation. So I'm gonna very briefly talk about our activities at Uppsala University regarding sodium-ion batteries, but also our a bit history, activities, and goals at Altris, which is a spin-off company aiming to commercialize sodium-ion batteries. So as you see, the title here is From Fundamental Research to Commercialization. So what we do at the university is very much fundamental research, trying to understanding different aspects of batteries. And then we try to bring that information and knowledge to industry. So I guess if I can, people here are very well aware of that we need more and more batteries. There is no return point on that, and this is clear to everyone that there will be more batteries used in different applications, not only in transportation, but also in other sectors, which basically means that we need access to raw materials more and more. And this is mainly regarding those elements used in lithium-ion batteries like cobalt, nickel, graphite, copper. And this will be, and this is already today, a pressure on industry to have access to raw materials for battery industry, which will lead to some economical pressure. The battery pack price actually increased this year for the first time after many years that it has been decreased. And also this may lead also to some geopolitical issues to have access to those elements. So the idea here is to move to naturally abundant elements. So just basically that green area to use naturally abundant elements like iron, manganese, and titanium instead of cobalt, nickel, and copper. And this together with moving from lithium to sodium can make batteries much more sustainable. So if I very briefly summarize what we do in my team at Uppsala University, where we work on sodium-ion batteries, I can mention 4 different categories. We work quite much on understanding of aging in batteries, what happens when batteries age. And to do that, we use a lot of different synchrotron-based methods, specifically X-ray photoelectron spectroscopy at synchrotron facilities in Sweden, in Germany, in Japan, and different places. We do also a lot material development, and that includes electrode materials, anode and cathode materials, and also electrolyte materials for sodium-ion batteries and lithium-ion batteries. And part of activity from my team led to this spin-off company, Altris, which was launched in 2017. So just to give you a few examples, one is this cathode material, Prussian white, which we started working on this in 2015, where we could actually synthesize this material in really low cost, low temperature method in upscaled format. So the interesting thing with this material is that it has quite high theoretical capacity, almost 170 milliamp hour per gram, which is then in the range of lithium iron phosphate, for example, for lithium-ion batteries. And it does contain only abundant elements like iron, carbon, and sodium. So when we got this achievement, we started this spin-off company, Altris, in 2017. And the motivation for us was that we believed that this material could get into commercialization of sodium-ion batteries, because it's very easy to make it, or basically the method that we developed enables us to make this material in larger scale, in low cost, low temperature, which is fantastic for commercialization. We consider this as a like drop-in solution, and with relatively high capacity, and it works in wide temperature. This was the motivation when we started, and it was fantastic to see that this summer, CATL, which is the biggest battery producer in the world, announced that they are going to have commercialized sodium-ion batteries, which is a great news for the whole battery industry, especially sodium-ion battery. But also they specifically mentioned that they are using Prussian white as cathode material in their sodium-ion batteries, which is good news for Altris. And this also gives us more confidence that the material that we have been working on for a few years is an excellent option to use in commercialized sodium-ion batteries. So with this, Altris has since some time ago put a goal to make a production capacity for Prussian white, or they have registered it under the name of FENOC, which is Prussian white-based cathode material. And there have been like a upscale production at Altris, but the plan is to have capacity of production of Prussian white equal to 1 gigawatt over batteries in 2020, which is a big goal for Altris, but we think this is achievable. This is one example of material which has been studied in my team. The other one is electrolyte related, which we have been focusing a lot on developing fluorine-free, non-flammable electrolyte. And for the first time, we show that sodium bulb can be used actually as electrolyte salt in sodium-ion batteries. And in few recent studies, we have shown that sodium bulb can be used in TMP, TEP, and other phosphate solvents with relatively good ionic conductivity in range of 5 to 8 millisieverts per centimeter, and makes the electrolyte non-flammable, which is another advantage of for sodium-ion batteries that we are developing, to have such fluorine-free and non-flammable electrolytes. And very recently, we have demonstrated that with such electrolyte in full cell sodium-ion batteries with Prussian white cathode, we can cycle battery up to 2000 cycles. There is definitely some capacity fading. So we are reaching 50% of the initial capacity after 2000 cycles when we cycle at room temperature. And this is something for us to understand and work more on that. And that is why we go to synchrotron-based measurements and number of different spectroscopy measurements to understand what are the aging in sodium-ion batteries and how can we suppress aging. So with that, I'm going to also give another example of what we have been doing on understanding of aging in sodium-ion batteries. So I'm sure many of you know about SEI in batteries, solid electrolyte interface in batteries, which is a passive layer to make batteries kinetically stable. So here's a schematic of a battery where you have the negative electrode and the electrolyte exposing the negative electrode or the anode. So when you start charging the battery, you have electrons move into the anode, and then the solvent and salt molecules will reach the anode. And since the potential of the anode is beyond the stability, there will be a solid layer, which is called SEI form, on the surface of anode to make the battery stable. So this layer, of course, as you know, is formed in expense of charge consumption. So we want this layer really, really stable over time at different conditions. So, and one major agent that we have shown recently is that when you have SCI at the positive state, or the battery at the positive state, part of this SCI can be dissolved back to the electrolyte. So this SCI dissolution is a major issue when it comes to aging in batteries, specifically in sodium-ion batteries. So we have been using different methods, including galvanic static cycling, but we have modified the method a bit to combine it with extended pause time to see what happens when you make a long pause time in a battery. And we have used that for different pauses. And then we have shown that this SCI dissolution is very much dependent on the volume of the electrolyte, which is another indication that this agent that we observe is related to SCI dissolution. So following this type of method to understand SCI dissolution and aging in sodium-ion batteries, we have recently shown that for different electrolytes, these are like just different carbonate-based electrolytes, PC, ECPC, and ECDC, that we can measure the amount of capacity loss over pause time. And you see, the longer the pause time is, the higher the capacity loss is. But you can see that also if you look at the y-axis, we are talking about very small capacity loss, microamp over. This is very small, tiny capacity loss that we observe during pause, during relaxation, but this is definitely important to address and suppress if we are aiming to commercialization of sodium-ion batteries. With these methods, we can detect the issue, the problem. We can understand how this is related to SCI, and we can see how the chemistry of electrolyte is influencing SCI dissolution. So our aim is to address this by formulating electrolyte chemistry to address SCI dissolution. So this was a short presentation as I was asked for, and with this I would like to thank my team at Uppsala University, who all these results I have shown here is basically it's due to the great people in the sodium team at Uppsala University. So thanks to all PhDs and postdocs in my team, and thank you again for this invitation. I'm happy to take questions.
Thank you, Professor Yogesh, for brief introduction of the activity which your group is doing and what we specifically looking for future. Now, just to have idea of another component of battery, we have with us now Professor Ryoji Inada. He is an associate professor at Department of Electrical and Electronic Information Engineering at Toyohashi University of Technology, Japan. He received PhD from TUT in 2001 and subsequently arrived at the post of research associate at the same university. He was also awarded research fellowship for young scientists from Japan Society for the promotion of science in 2001. His current research area is the development of functional ceramic material and their application in electrochemical energy conversion and storage devices, particularly for materials and processing of ceramic-based all solid-state lithium-sodium batteries. So he have also been engaged in research and development for high-temperature oxide superconducting wires for power equipments. As a non-research activity, in 2017, he also served as a senior science and technology policy fellow at the Cabinet Office of Japanese government and experienced the task of planning science and technology policies in Japan. Considering his vast experience in solid-state batteries, I welcome Professor Ryoji Inada to discuss and to give his view about his work and solid-state systems and sodium-ion battery. Professor Ryoji.
Can you hear me?
Yes, we can hear you.
Okay, okay. I will share my slide from now. Please wait a minute.
Yeah, please.
Can you see the slide?
Yes, very much.
Sorry for interruption. It's a kind request, Professor Nada, if you can share, also open your video.
I'm not the second speaker. I'm not the second speaker. I think
you may start.
Mr. Inada, actually what we are saying is, if you can switch on your video.
Speaker.
Switch on your video, actually. Switch on your video.
You can switch on your video, your camera.
Sorry.
Professor Ryoji, you can switch on your camera, please, if you want. Otherwise, okay.
Okay. Oh, sorry. Oh, can I start the presentation?
Yes, you may start.
Okay. Thank you again, Dr. Sharma, for your kind introduction. And I also thank to all organizers of this webinar for inviting me as a speaker. Good afternoon, everyone. My name is Ryojin Nada. I'm an associate professor in Toyohashi University of Technology, Japan. In my talk, I will briefly introduce the ceramic solid sodium-ion conductors, particularly for solid-state battery applications. As you recognize well and similar as the lithium-ion battery systems, the replacement of the liquid electrolyte to solid ceramic electrolyte is one of the effective methods to improve the safety and the reliability of sodium-ion batteries, because we can avoid the possibility of leakage, rupture, and ignition troubles. Due to the ceramic nature, solid-state batteries can achieve good cycling performance and stable operation even at the high temperature range. In addition, it is possible to achieve high volumetric energy density of batteries because the bipolar type battery composed of many single battery cells is easily assembled in a single package. But there are many issues to be solved to achieve high performance in solid-state batteries. Key material is a solid ionic conductor used as a solid electrolyte in batteries. This solid electrolyte material has not only the high conductivity at room temperature, but also good deformability for intimate interfacial properties of the particles, the chemical and the electrochemical stability. Using this solid electrolyte, we have to form the good solid-solid interface with both cathode and anode materials. And today, we have a lot of types of ceramic sodium-ion conductor, such as sulfides, oxides, and halides or something like that. But this table is the summary of the comparison of the properties of sulfide-based solid electrolyte and oxide-based ones. At first, the sulfide-based one, sulfide-based electrolyte has a higher room temperature conductivity than oxide-based one, and the sulfide can be deformed more easily compared to oxide, which is suitable for intimate contact with both cathode and anode active materials. However, the sulfide is generally very reactive with air and moisture, and its handling is very, very difficult. Of course, there are some electrochemical instability issues. On the other hand, the oxide-based solid electrolyte has slightly lower conductivity than sulfide, and generally, high temperature sintering is needed for densification and reducing the grain boundary resistance, but it may cause an undesired side reaction with electrode materials. However, the chemical stability is very good, much superior to sulfide. This leads to easiness for handling. And on the other hand, since 2010, many kinds of sulfide-based sodium solid electrolyte with a conductivity well above 1 millisiemens per centimeter, as shown in this graph, at room temperature range. Among them, the tungsten-doped sodium thioantimonate and this composition show with the cubic crystal structure show the very high ionic conductivity above 30 millisiemens per centimeter at room temperature. This is well above current liquid electrolyte for sodium-ion batteries, I think. Sorry. And similar as the sulfide-based lithium solid electrolyte, sulfide-based sodium solid electrolyte is very easy to deform. Modulus of sodium thiosulfate, as shown in this graph, is slightly smaller than lithium thiosulfate, lithium thiophosphate, sorry. Most of sulfide-based sodium solid electrolyte react with water in air to form a toxic hydrogen sulfide gas, as shown here. But this gas, toxic gas formation can be suppressed by controlling the composition of solid electrolyte materials, as shown in this graph. Okay, next, I'd like to move the topic of the oxide solid electrolyte. The history of the oxide-based sodium solid electrolyte is very old, as you know. Even in 1970s, the two famous materials, sodium beta alumina and nasicon, was discovered, and their room temperature conductivity attained to above 1 millisiemens per centimeter at room temperature. These two materials have also a wide electrochemical potential window and stable against the sodium metal. And the sodium beta alumina is practically used as the electrolyte in NAS battery developed in Japan, which is operating at 300 degrees C, composed of the melted sulfur cathode and the sodium anode. And the layered type material has been reported in 2010. This material has lower processing temperatures compared to other two old solid electrolyte materials, sodium beta alumina and nasicon. Using a nasicon electrolyte, the solid-state sodium metal battery operating at the lower temperature was fabricated successfully. This is reported in 2017. And the cathode is a sodium titanium phosphate and mixed with the sodium conducting polymer and the carbon black. The electrolyte is nasicon, and the anode is a sodium metal, but between the solid electrolyte, nasicon solid electrolyte and the sodium metal, the interlayer, polymer-based sodium-ion conducting polymer interlayer is inserted to form a good interface between the solid electrolyte and the sodium metal. As a result, this battery sample operates at around the 2 volt and shows very good cycling performance at 65 degrees C. Of course, this is a very basic research. The interface issues between the sodium beta alumina and the sodium metal anode at room temperature range is also investigated. When we achieve the sufficiently low interfacial resistance below 10 ohm square centimeter between the sodium beta alumina and the sodium metal anode, the sodium beta alumina symmetric cell has much higher tolerance for dendrite growth into ceramic solid electrolyte compared to the lithium metal and the garnet type LLG or solid electrolyte system. Although there are many issues to be solved for the practical use of sodium metal anode, this result indicates the possibility of fast charging solid-state sodium metal battery in future. Okay, this is the last slide for my presentation. We are now focusing on the layered type sodium solid electrolyte, MTO, as shown here. Although the conductivity of this material is slightly lower than nasicon and sodium beta alumina, this material is stable against the sodium metal and its processing temperature is much lower. And recently, we found that several layered sodium oxide cathode material is thermally compatible with this material up to 700 to 800 degrees C. We are trying to fabricate the solid-state batteries by simple co-sintering process now. That's all. Thank you very much for your attention.
Thank you, Professor Inada.
Yeah, thank you.
You have briefly introduced different solid-state ionic conductors and how one can make sodium-ion batteries if he is really interested in solid-state batteries. So now, in continuation of presentations, we have now Professor Prabir Barpanda from Indian Institute of Science, Bangalore. He has done undergrades from ceramic engineering at National Institute, Rourkela. Then he moved to ISC Bangalore as a project assistant for working on some of the materials. Soon after, he obtained a British Chimney Fellowship to pursue MPhil degree at University of Cambridge in affiliation to the Wolfson College. Then he moved to the USA for his PhD from the Rogers State University of New Jersey, where he has working on halidated activated carbon-based supercapacitors. Under the Professor Gigi Amatusi, one of the well-known person in energy storage devices. After say 4 years, he moved to North America and moved back to, after staying in North America for 4 years, he moved back to Europe to do for doing postdoctoral work with one of the renowned person in this area, Jean-Marie Tarascon and Professor Michael Armand at the University de Picardie, Jules Verne, France. Following, he moved to the University of Tokyo as a JS-Space fellow, conducted his second postdoctoral training under the guidance of Atsuo Yamada. After 10 years long stay abroad, he moved back to India, and now he is an associate professor at IST Bangalore. He is directing a lab which is focusing on material synthesis, structure, and electromechanical investigation of all inorganic inserts of material. So he is one of the pioneer worker in sodium-ion batteries, working for a long time, and we would be happy to listen to him. Professor Prabir, it's over to you.
Thank you very much. So at the outset, I would like to thank the organizer, Indi Energy, for this nice small symposium. And it is a pleasure to follow Professor Yunesi and Professor Yanada. So now actually I would like to, in my presentation, I want to talk a little bit overview about the anode material for sodium battery and some prospects and status. So my name is Prabir and my lab name is Faraday Materials Lab at MRC ISC. So today I want to just show you we all know the basics of this rechargeable battery. Essentially, we have a positive electrode and negative electrode, and here there is a intercalation of or deintercalation of the alkali ion. And as a result, in this rocking chair mechanism, basically we get some electron flow in the outer circuit, and we use that for our energy storage for energy application. Now, when we talk about this battery materials, in general, if we take all the component of the battery materials, the cathode or the positive electrode account for highest amount of cost, almost 35%. But one important part here is also the anode material. As a cost wise, it is not very important, only 6%, but it is very important part of the battery material. So since the invention, we have too many cathode materials. And I would say the success of the lithium battery, when we got the Nobel Prize, basically it can be credited to the formation of this carbon or graphite anode, because we all knew different kind of cathode material. It was the culmination of this anode material that really made the real life battery. Now, when we talk about the lithium battery and sodium battery, what is the main difference? The cost of this lithium, the crust abundance is very, very low. As a result, the lithium carbonate or the metallic grade lithium is very, very expensive. On the other hand, for sodium battery, the resources, the crust abundance is very high. As a result, the cost of sodium carbonate and sodium metal can be very low. As a result, we can develop something called economic post-lithium ion battery. And lithium battery was commercialized in 1991 by Sony in Japan. And this is the year, in 2021, CATL in China, they actually commercialized the sodium battery after 30 years of gap. Now, when we talk about the sodium battery actually assume an intermediate position between the very heavy lead acid battery and very light lithium ion battery. Now, this particular combination of this gravimetric and volumetric density is good enough to have different applications like stationary storage and also the small scale electric automobiles. Now, this diagram shows our beautiful globe, and this yellow mark shows different resources available for lithium-based salt. So here, Australia is very rich in lithium, and this is the golden triangle, Bolivia, Chile, Argentina, little bit in North America and China, and now we have Afghanistan, Kazakhstan, and so on. There are a lot of lithium resources, but you can see this is very sparsely distributed. On the other hand, sodium-based resources are very, very economic and they're uniformly distributed. As a result, it is very easy for all countries to use and develop the sodium technology. So, but one main problem about sodium batteries, we cannot use graphite as anode material. Unlike the lithium and potassium, we cannot use graphite here. Why? Because from theoretical calculation, Professor Goddard group has shown, whenever we try to intercalate sodium into the graphite, basically the formation energy, we can say it is the decohesion energy. Basically, when the sodium atom try to move away from each other, the straining energy when we take the graphite layer out of each other, and also the binding energy. So if we really combine all these things, unfortunately for sodium, the net energy, which is the net energy of formation, is positive. You can see for lithium, potassium, and so on, it is negative. For sodium, it is positive. As a result, it is really impossible to put sodium inside the graphite anode. So that is a big problem. But to circumvent that, we have different world of anode material for sodium battery. So today I will describe briefly about the overview of different kind of anodes for sodium-ion battery. So what we can think, anode material is kind of, some kind of empty bucket, I can say. And the sodium, I can consider like some water droplets. So when we try to use this anode, basically we try to fill the bucket with water. Like it's basically we're filling this anode with sodium and we're trying to taking it back again. So there are basically three main kind of anode material that is possible. One is intercalation based material, which we can show like some hard carbon where the sodium can go in, or some titanium based oxide where sodium can go in. This is kind of an intercalation and deintercalation mechanism. And the second one is alloying or de-alloying, where the sodium can react with some metal to form different intermetallics and alloys, and again it can break and it can go back to previous position. And the third mechanism will be conversion, where the sodium can react with some compound like pyrite to form a completely new material like sodium sulfate and iron. So today I want to just give a brief overview of different kind of mechanism. So one slide each. So the first one is intercalation based anode. Now here you can see this is graphite. Graphite is basically, we can imagine a long graphene planes. They are basically stacked against each other. And here the interatomic interplanar distance is very, very low. So lithium can go in, but in case of sodium, it is difficult to go in. But when we make hard carbon, which is basically, you can think of like a disordered graphite with some broken planes, some localized graphitic domains are there, then it can lead to something called house of card model. And here the interplanar distance we can increase to 3.7 to 4 angstrom. As a result, sodium can easily penetrate. So this graphite has been shown, this hard carbon has been shown to really intercalate and deintercalate lithium very, very nicely, sodium very nicely. As a result, we can get capacity around 220 milliampere per gram. And also here it is shown for sodium battery, it is also important to develop good electrolyte, good additive, and also the different kind of binder, particularly CMC binder has been shown to be very, very effective to get some good electrochemical stability. So with this, actually with using hard carbon, it is easy to form high capacity, economic and reversible anode for sodium ion battery, and which can be very, very low cost economic candidate also. And coming to intercalation anode, also it is possible to have something called titanium based anode. So basically titanium based redox can be useful for different anode material, as it is shown for lithium battery with Li4 Ti5O12 spinel kind of anode. Similarly here, basically we can have different kind of titanate like rutile TiO6, lithium titanate, sodium titanium oxide, and sodium titanium phosphate, and so on. So basically, using different kind of titanium anode, it is possible to get titanium intercalation redox system. One example here is shown is Na2Ti3O7. So this material basically works as the lowest voltage anode material, operating around 0.3 volt versus sodium, and it gives capacity around 150 milliampere per gram. So very, very decent. Now, if we do the ball milling, we can further enhance the capacity to close to 200 milliampere per gram. So here, basically, initially we have Na2Ti3O7, and when we try to insert 2 more lithium, it can become Na4Ti3O7, and thus 2 sodium can come in and out, and 2 electron reaction can give to 200 milliampere per gram capacity. So these are 2 classic examples of how we can use intercalation based anode for sodium battery. Now moving on, the second class is the alloying anodes. So if we see this portion of the periodic table, basically sodium, so carbon is the hard carbon, forget it, but below that, this intermetallic semi-metallic component, it is possible that sodium can react, one sodium can react with silicon germanium, around 3.75 sodium can react in it, and around 3 sodium can react with this antimony, bismuth, and so on. As a result, what happens, it can form different kind of alloys with this all these kind of elements, group 14 and 15 elements. So if we see this diagram here, particularly for silicon, the capacity is not so good, silicon germanium, but when we go to this NaX kind of material, particularly with phosphorus, we can give rise to very, very high capacity. So over 2500 milliamp per gram. And with this, actually, it is possible to design different kind of alloying-based anode material. I want to give you two examples. One is with antimony, one is with phosphorus. So the first one is with antimony. Basically, sodium react with Sp to form Na1Sp, then Na2Sp, then finally Na3Sp. So basically, 3 sodium can react to form Na3Sp, and as a result of 3 sodium reaction, it can give rise to very high capacity, close to around 600 milliamp per gram with the voltage around 0.7 volt. So here at a low voltage, we are getting very good capacity with good cycling stability. So this is one potential anode material for sodium battery. And the most important example here is the phosphorus. So phosphorus basically exists in 3 forms: the crystalline form, the red phosphorus, and the black phosphorus. The red phosphorus is very, very stable. And once again, when we use just red phosphorus, it can react with sodium to form Na3P. And because the phosphorus has very, very low weight, so it can give rise to very high capacity, around 2000 milliamp per gram. So these are some examples where we can use this group 14 and 15 element to design some alloying and de-alloying kind of anode materials. Now the next example is conversion type anode material. So just to give an example, some iron, some metal oxide and metal sulfide and metal nitride can be useful for anode material based on conversion reaction. Here there is a particular example of iron sulfide or pyrite. So basically we can use iron oxide nanocube, and we can react this iron oxide with sulfur gas. If we react with iron oxide with sulfur, it forms sulfate gas and iron sulfide product. So this iron sulfide product can give rise to different morphology. And when we react this with sodium, basically sodium can interact with this iron sulfide or pyrite to form NaFeS2, and followingly, it can actually decompose to form Na2S and metallic iron. And this can actually go back to the system during the charging discharging. So this is an example how using conversion reaction, we can get some capacity around 600 milliamp per gram, and it is fairly stable in operation. Now, one point to remember is, in case of conversion reaction, it is possible to have multi-electron reaction, and which can deliver large capacity. Nonetheless, it is thermodynamically limited, and the conversion anodes suffer from very large polarization between charge and discharge, and also it has very high irreversible capacity loss. So very honestly, these conversion reactions anode are not very suitable for practical application, particularly when we need high rate charge discharge operation. Now coming to the end, one more kind of anode material can be developed, which is called organic anode. Nowadays, people are talking about a lot about sustainability. So some bio waste kind of thing we can use. So some agriculture waste also we can use, and this kind of compound, basically organic compound, we can take this and we can react with sodium. So basically this double bond and all this thing can break, and it can form a single bond with here and one bond with sodium. As a result, all the double bond can break, we can get some sodium based compound, and again some more sodium can also go here. So here I can show 0 sodium to 2 sodium to 4 sodium. Basically 4 sodium can go in and out like that. And with this, actually, we can get some nice low voltage operation with capacity around 300, which is very close to hard carbon, and very good cycling stability. So with this, I would like to summarize my talk. It is possible to have designed different kind of anode materials. And in summary, this is taken by Professor Komawa's paper, and where in the review it is said this is the hard carbon and this is the phosphide kind of material and some alloying kind of material. Here we can see actually we can get some very, very good energy density against different kind of cathode material. With this, I would like to come to an end and say that sodium battery, basically it is a combination of research on cathode material, anode material, and electrolyte. And in electrolyte particularly, the effect of additives and also the binder, they are very, very important. So combining all of them, it is possible to design some real life sodium battery for applications where we don't need really very, very high gravimetric and volumetric energy density. With this, I would like to conclude, and thank you very much for your kind attention. Thank you.
Thank you, Professor Praveer, for nicely given some idea of anode materials which can be used for sodium-ion batteries. And I'm sure many of audience might have seen different type of material. They might be working in different type of material as far as anodes are concerned. Now, for the next 10 to 15 minutes, we will be discussing about different prospects and challenges in sodium-ion batteries. I request every participants to write their queries in chat box if they have. We have all three speakers with us. We will be able to answer as much as possible within the given time. So I take a liberty being a moderator to start some discussion. I'll start discussion with Professor Yogesh that I mean, where you see the sodium-ion battery at present, Professor Yogesh. If you compare with lithium-ion batteries, in fact, Kettle has announced their inception or their product in 2022 probably. So, but still there are some challenges which we need to look forward. We need to see how we can come and reduce those challenges and develop a better battery, which will be cheaper battery and for everyone battery. I mean, as you know, the lithium is a scarce material or element. We cannot have lithium everywhere, but the sodium can take example and can take a something like a huge importance and advantage over lithium, that the sustainability and availability is there for sodium. So now it is to you, please.
Sure. There are, of course, challenges, and there will be challenges, and the same applies to lithium-ion batteries. So this is science and technology. There will be challenges, and that's why we do this. So, but the reason that I think the reason that the industry is much more positive now today is towards sodium-ion batteries is that because now everyone is facing the issue with access to raw materials and the reality of increased production of batteries, lithium-ion batteries, which has motivated people to look at sodium batteries based on naturally abundant elements. I think that's the motivation. And of course, there are many chemistries, many different chemistries when it comes to batteries that people could work on it. But the unique thing with sodium-ion batteries is that it's a drop-in solution for the same factory that we have for lithium-ion batteries. So we can use the same factory, the same lines, the same methods, basically, to produce sodium-ion batteries. And that's a big advantage of sodium-ion batteries compared to other chemistries. And because of that, I think the commercialization of sodium-ion batteries is happening and will happen. So there is no doubt on that. So, but if you compare with lithium-ion batteries, of course, we need to have more understanding of, if you ask me, more understanding of interfacial reactions, a CI on the anode side or CI on the cathode side, to address aging in sodium-ion batteries, to make them a longer life. I would say that's the main challenge. I don't hear you now.
So the biggest challenge, you believe that rate capability is one of the biggest problem in sodium-ion batteries?
No, I didn't say rate capability. Actually, since sodium ions can be dissociated from solvent easier compared to lithium-ion chemistry, actually rate capability is believed to be better in sodium-ion batteries compared to lithium-ion batteries. I think the problem is the interfacial reactions, which leads to parasitic reactions. That is something that needs to be addressed. So when it comes to SEI, for example, on the anode side, we need to make it more stable in sodium-ion batteries. And the reason is that these SEI species in sodium-ion batteries are more soluble in the electrolyte compared to SEI in lithium-ion batteries. So that leads to...
Professor Yogesh, we have one question from audience. How does the SEI dissolution reduce the capacity?
So SEI formation is a reversible irreversible reaction. So you consume electron, you consume charge, you consume electrolyte to form this solid electron interface. So every time that SCI is destroyed or dissolved,
So
and you need to.
Yeah. So do you? Sorry. So you mean that it is the sodium ions are not conducting to the SCI, and it is limiting this kinetic factor?
No, there of course there has to be sodium ion diffusion to the SCI, and that is, and for sure, if it doesn't happen, then there is no battery. The concept is the same as lithium-ion batteries. We have this solid electrolyte interface where ions diffuse. Ions from the electrolyte will diffuse to SCI, and then there will be diffusion of ions to the electrode. So that needs to be reversible. So it's like a thin layer of solid sitting on the surface of anode material, and there will be ion diffusion through that. The problem is that this thin layer is less stable when it comes to sodium chemistry compared to lithium chemistry. So we need to make it more stable to make sure that it's not dissolved, because if it's dissolved in the electrode, you need to reform it. You need to consume energy.
Right, Professor Yunusi. Another question to Professor Prabir Barpanda, we have from Sonali Garg. There is a question, by hard carbon, what do we mean? Can activated carbon be the examples of hard carbon?
Okay, so the carbon material, we can divide like soft carbon and hard carbon. Basically, soft carbon are material which is these are not graphitic, but if you heat at very high temperature at pyrolysis, it can be graphitized. Hard carbons, on the other hand, some carbon material which has basically small graphitic domains are there, but even if you heat at very high temperature, it will not be graphitized. So activated carbon, you cannot call it hard carbon, not necessarily.
I mean, from commercial point of view, why anode material is only stuck to hard carbon? There is one again question from Milan.
Okay, so for the sodium battery, as I mentioned, the size of the sodium and the Stokes radius is in such a way it cannot go to graphite. And hard carbon we can easily make. This is basically in large scale we can make. It is very, very stable and it is very, very economic, and it can show some good sodium reversible intercalation and deintercalation.
So in this means only hard carbon, only the material, anode material as of now for sodium ion batteries, commercial viability, there is use in hard carbon only. Professor Prabir, I think we got stuck somewhere. Am I audible to everyone? Yeah. Hello, Prabir, are you there? Okay,
yes,
maybe.
please go ahead.
Yeah. So this means hard carbon is only material which can be used as an anode material in commercial sodium ion batteries as of now. Okay, well, maybe I can ask Professor Yunusi about the hard carbon. Do you think only hard carbon is a material for commercial sodium ion battery, or there any other anode material can be used?
So far, I mean, only hard carbon is really viable because of the economy and the low cost of production, material stability. If you see all of them, hard carbon is the best choice so far. But people are coming up with other material like sodium titanium oxide and other kind of thing, which maybe in future we can have better choices. But honestly, this conversion and alloying kind of anode material, it cannot give very high rate performance like an intercalation based system. So in that way, just like lithium, maybe sodium battery also will be limited to intercalations anode only. Maybe
there is Professor Uttam Kumar Chanda is asking, can silicon be used as an anode material?
So actually I showed silicon can be used, but it can give rise to very, very low capacity. So only one sodium silicon, only one. But if we use say phosphorus or antimony, it can give to multiple electron reaction and the capacity will be very high. So silicon is good for lithium, not so good for sodium.
Pratik Bhojane is asking, if the layered materials or interlayer can be tuned with the anode, can it solve the purpose?
Yeah, in theory, yes. if you can
Yes,
tune,
in
but
theory, yes.
it is difficult to tune like that.
Yeah, so again, we say that if hard carbon is being used, that only there is a possible intercalate sodium and at the surface as well as to the interlayer. So Pratik and everyone, I think hard carbon is only the material for anode as a anode. Professor Yonasi, one audience is asking, is there any chance of artificial SEI in sodium-ion battery? Artificial SEI?
Sure, yeah, that's an interesting topic. Not only for sodium-ion battery, but also for lithium-ion batteries, to make sure that you can have better SCI by having artificial SCI. It's interesting, and that might be even more relevant when it comes to sodium-ion batteries, where we face the issue with the SCI dissolution. But we all know that artificial SCI usually means higher cost a bit compared to in situ formation of SCI. If one could make excellent SCI ex situ or artificial SCI ex situ or in situ, sure, that would be interesting approach.
So there is one question again: which sodium electrolyte formulation is commercially acceptable in your view?
I think the common trend is that people have been basically copy-paste from what we have had in lithium-ion chemistry. The carbonates are used now in sodium-ion batteries and PF6-based salt. But I think that's actually one interesting question, that this is where we think we should be a bit more careful. The fact that the sodium chemistry is slightly different than lithium chemistry when it comes to electrolyte means that we might have possibility actually to use new chemistries, new electrolyte chemistry, which might be much more interesting compared to lithium chemistry. There are minor differences that we should work on, that, like the solvation structure, the solution of SCI, the fact that we use hard carbon, not graphite. So those will open up actually opportunities to use a new solvent and salt chemistries. For example, that's exactly the reason that we have been working on sodium bulb to make fluorine-free electrolyte. So we can make a SCI a bit more passivating actually in this case, and have it more stable.
So based on your experience, do you recommend some specific formulation for sodium electrolyte?
There are people working on that. There is no specific that I can recommend right now. This is a question. Yeah.
So Professor Ryoji, what do you think, which specific solid state ionic conductor can take the next level of sodium or lithium ion batteries? If we talk about solid state batteries, Professor Inada?
Yes.
Yeah.
Yes.
Which composition or which compound you feel that has the potential of a commercial material in solid state batteries?
For solid state battery?
Yeah.
Electrolyte?
Yes.
It's a very difficult question. For solid state lithium battery, some Japanese companies produce the lithium thiophosphate commercially.
Okay.
So, also some Japanese or other countries companies start to develop the commercial oxide lithium ion conducting materials, LLZO, garnet, some company.
Right.
But I don't know these materials is well distributed in the consumer in all over the world. I don't know.
Right.
I think these two materials is commercially available. On sodium ion conducting materials, we don't have any. Yeah.
So in your view, the research is going on. There is no sort of a commercial product or commercial compound is can be used.
Yes.
Right.
Yes. Right.
Okay, Professor Yonisi, there is one more question, very interesting question, I think I should say. What difference of percentage cost we can say that we are saving in manufacturing of sodium-ion battery in comparison to lithium-ion battery? For manufacturing process.
Yeah, what was the question for me?
The question is, what percentage of money we are saving when we manufacture sodium-ion batteries in comparison to lithium-ion?
This, I think it's a bit difficult question to answer because the sodium battery industry is not as mature as lithium one. So this requires further real production of sodium-ion batteries to see how much we save. So, but one could look at number of important cost reduction. The fact that we don't use expensive raw materials, and that includes cobalt, nickel, and copper. These are very three important elements that are getting quite expensive. So we're going to save costs there. Another aspect is, if you look at the sodium batteries or sodium cells that Altris is developing, everything is based on water soluble binders. So there is no need for NMP. That's another very important cost reduction where the production line will be much easier to handle. We don't necessarily need a dry room, let's say. That's also another important cost reduction. So those are interesting points to look at it, but it's very difficult to say that what is really the percentage.
Yeah, but as for the raw material, at least manufacturing processes will be similar as lithium-ion processing. However, the raw material will be, I think, 20 to 30% cheaper, as we don't use copper current collector in sodium-ion batteries. Sodium-ion cathode is supposed to be cheaper because it is made up of sodium-ion, or we call it salt batteries. In India, we will call it salt batteries because sodium can be taken from the salt. And then that's what we believe, it's a 30% cheaper than the lithium-ion batteries overall, but because the energy density might be different, but it is very difficult to say per dollar, per kilowatt hour, what will be the dollars in dollars the cost. So, but essentially the raw material and its cost will be really less as compared to lithium-ion batteries. There are many questions, but I'm sorry, but I cannot take everyone. So I am selecting any important question related to technologies of sodium-ion batteries. If there are any, if I'm sorry that I'm not able to take all the queries because we have only fixed timing. In fact, we are over by 7 minutes. There are many questions which I really don't know whether I will be able to take them or not. But there are some magazines. I don't think so. It is. Yeah, there is one query from Love Dasaria. Is there any chance of SEI formation towards the cathode side, Professor Yunusi? SEI towards cathode side.
Yeah, sure. That, I mean, similar to lithium-ion batteries, there might be surface layers formed on the cathode side, whether we call it SCI or CI. This is a possibility. But the fact that the redox potential of cathode materials in sodium-ion batteries is slightly lower than the one in lithium-ion batteries means that there is a little lower chance to have such layer on the cathode side. So we are talking, when it comes to cathode for sodium-ion batteries, we are talking usually in the range of 3 to 4 volts. That means most electrons.
We have one last question from audience side. Mr. Pareen Seth is asking, Professor Yunusi, considering the world as a market for sodium-ion batteries, which region, Europe, Asia, USA, will accept faster penetration of sodium-ion battery? What would be the major regions for the same? These are the two queries.
An interesting and difficult question. I think everyone is interested to have sodium-ion batteries. So it's a matter of who is faster and more successful. I mean, I think Asia is producing now, given the news by CATL and so on, and given the history that the major battery producers have been in Asia, I think Asia will quickly be very big in producing sodium-ion batteries. On the other hand, if you look at, for example, the approach that Tesla has had to use LFP in some of their cars, I wouldn't be surprised if there will be sodium-ion batteries production in the US, and there are a number of interests and initiations in Europe also. So it's happening everywhere.
So there is one, actually one last question. In fact, I should say one more time last. what are the application, Professor Yunus, you see for sodium-ion batteries at present, considering the energy density, power density of the battery, present commercial sodium-ion or to be commercial?
I think everyone is aiming for a station in a storage at this stage, or that's what everyone was saying up to a few months ago. But we can also say that people are now more positive to sodium-ion batteries, especially after the announcement by Tesla that they are using LFP in their cars. That means now with sodium-ion batteries, we can have more or less the same energy density as LFP-based lithium-ion batteries. So there is possibility for sodium-ion batteries to move to some of transportation application also. Not necessarily very expensive cars, but one could think of lower cost electric vehicles where sodium-ion batteries could have a role.
Okay, thank you, Professor Yunesi. So just to summarize our discussion, what should I say? I mean, from our discussion, I can say that the hard carbon is only anode material for sodium-ion batteries at present, which can be made by easy and cost-effective methods. So in this case, Indi Energy is doing great work, I would say. Second thing is that sodium-ion batteries has application in stationary storage, and if Tesla can use LFP battery in electric vehicles, then sodium-ion batteries also can be used in electric vehicles. So this open another application area, so stationary as well as electric vehicles. I would say three vehicles. I mean, e-rickshaws in India is a big market. Millions of e-rickshaws in India. So sodium-ion batteries can immediately replace this lead-acid batteries without any problem. Energy density, cycle numbers, people have shown up to 1,000 cycles, 2,000 cycles. So there is no problem with sodium-ion batteries to just replace this lithium-ion batteries. With these recommendations that sodium-ion batteries can be a good cup of tea in Indian context and Asian context, and the country where we don't have lithium. So country like India or Europe, whole Europe does not have lithium resources. Similarly, India does not have lithium resources. So in my opinion, whole Europe and whole Asia will go for sodium-ion batteries very quickly, and the penetration would be more as we have seen. And with all these recommendations of this panel discussion, now I will take leave, thanking every speaker from my side and thanking every audience. I'm sorry I could not take all the problems which you have mentioned in our chat box. I'm sure we will be able to answer your queries on email, which we already have with us. So we will answer all the queries, whatever we have today. So with all, thank you very much. Thank you. Now, Akash, it is up to you. Akash, you are not audible. Akash, you unmute your mic, please. Yeah.
Thank you, Professor Yogesh, for the introduction and for the. I would like to, first of all, a very good afternoon to all of you. I would like to first of all thank all the eminent panelists today for today's webinar. Professor Yunesi, Professor Praveer, and Professor Inada for giving the important insights on the development and commercialization of sodium-ion batteries at academic and industrial level. I would also like to thank all the guests and audiences of the webinar for patiently listening to these eminent panelists. I hope that you have gained some understanding about sodium-ion batteries from them. With lithium and cobalt becoming scarce element nowadays, the development of an alternate battery chemistry has become all more important. And we believe sodium-ion batteries could be the revolutionary battery technology that can sustainably build the future of India and the whole world. As knowledge sharing has always helped the world in development and improvement of any new technology, we will be coming with more such webinars in the future so that all important stakeholders can come together in a single platform and help build this important technology. In the end, I would like to thank the entire team of Indi Energy for executing the webinar successfully in such short time. Last but not the least, I would like to thank our digital marketing partner, the Viral Nerd, for creating such amazing posters and videos in such a short time. Thank you all again for attending the webinar. Cheers. Have a great day.
Yeah, thank you. Thank you, everyone. It was really a nice discussion. We will meet again and again for dissemination of the information about sodium-ion batteries. We need to take it to the next level. So thank you all. Thank you for your valuable time. We will see you again. See you soon.
Okay.
Bye. Bye-bye. Bye-bye, Inara. Bye, Barpanda. Yeah. Thank you. Thank you. Thank you, everyone.